Hello, my name is Judah Rosno, and this is my analysis from case study 2 talking about fixed supports. In this experiment case study, our objective was to quantify the impact of boundary condition compliance on simulation accuracy. In layman's terms, how does fixed supports on SolidWorks differ from fixed supports in real life? Short answer, quite a lot. In this case study, we had two setups. We had a straight bar and an L bar, as you can see on the left and the right. We mounted them so that their loads would be roughly in the same spot every time, comparable to each other, with the same loads being applied with varying wrenches and whatnot that we could find in the Maker Hub. We applied a consistent load spot and measured the deflection using ImageJ. For our simulation, we used a fixed support on one end and then applied a load on the other end. We made the length in our experiments. So this being where we applied the load experimentally and then how we were fixing it. This way we could actually compare the simulation with our experiments. As well as in our simulation, we added a curvature-based mesh and added mesh controls around our stress concentration being the hole in the bar. To verify, to see what ballpark we should be in, we used kind of some back-of-the-napkin calculations, got the inertia using the parallel axis theorem, and used a mechanics of materials deflection equation to see kind of where we should be at, and then ran that for all of our different loads. And in that, the simulation actually underpredicts what the hand calculations predict with an average percent error of around 10. This could be for a few reasons. A lot of times these hand calculations have built-in factors of safety in them as to overestimate what is actually going to happen so that we're safe. Our straight bar deflection was a lot closer. However, this time the simulation overestimated what was actually going on with the straight bar. And then with the L bar was a lot closer to the hand calculations, and the simulation therefore underpredicted with an average percent error of around 9 to 10. To kind of combat this with our simulation to kind of get it a little bit more accurate, kind of took the best of both worlds with the horizontal clamping of the straight bar and vertical clamping of the L bar. And so you can kind of make this shape, and doing this reduced our percent error from around 5 to 10% to around 1 to 2%. So it's a much more accurate way of modeling what a fixed face is actually like in real life. Testing setup flaws, we only tested one L beam and one straight beam. This can lead to some errors of not every beam being the same, as well as we did do a few trials. However, we realized later that we were likely in the plastic deformation loading phase of the bar ever so slightly. So that could lead to some errors with some differing modulus of elasticity, and vice versa. Varying things can happen from that. So in conclusion, things in reality are a lot different than they are in SolidWorks, and it's important to keep that in mind when you're modeling and using simulations, especially with fixed geometry. I mean, nothing ever is really truly fixed. I mean, we can get as close as we can. However, it's highly unlikely that things are actually completely fixed. Thank you.